Your calendar says 103. This is actually going on 104 because I didn't account for the title page. If you already wrote 103, it's not that big of a deal. But in your ISN on 103, I want you to put 6 weeks, and then this will go on 104, and then I'll adjust the calendar a little bit. All right, so we've talked about surface area and volume of pyramids, cylinders, cones, and prisms. And today we're going to look at spheres. Okay, so what I have here in my hand is a sphere. Okay, that shouldn't be any big shock. These are not brand new to you. These formulas probably aren't even aren't brand new to you. But this is a sphere. We'll look at this a little bit more as we go along. But it's not like a what? What do you mean it's not like the Earth? Oh, yeah, no, it's not like the Earth. Okay, so first definition is the definition of a sphere. So the definition of a sphere is that it is the locus of points. Now that's a strange phrasing, I'm sure you feel, but we've used those words before. Does anybody remember what a locus means? It's not the bug, there's no T on the end. Okay, a locus of points is just a set of points. Okay, so I left the strange wording in there because you need to be exposed to those strange wordings for when they come up later. A locus of points is just a set of points. So it's a set of points in space that are a fixed distance from a given point called the center. The only difference between this definition and the definition of a circle is that space right there. Because the definition of a circle is the set of all points in a plane that are a fixed distance from a given point called the center. So it goes from a two-dimensional thing to a three-dimensional thing. So if you look at this pen, if the tip of the pen is like the center, right? And we're going to talk about a circle. So it's the set of all points in a plane that are the fixed distance. So this is my fixed distance, which is like my radius. So if I'm going to stay two-dimensionally and I draw like this, then I'd be drawing the circle. Does that make sense to you? When I switch from in the plane to in space, then I can go three-dimensionally. And then when I go like this, then I'm like coloring on the inside of a sphere. Does that make sense to you? Okay. So that's what's happening there. Because it's just like the sphere itself is like what you see. It's empty. Okay, it's just the outside part. There's not actually any thickness, just like with the circle. That ring doesn't actually have any thickness. Obviously, when we draw it, it has some, otherwise we can't see it, but that's, in theory, it doesn't have that. Okay, so this, on our picture here, this is my center. Right. And then a sphere, just like a circle, has a radius. So a radius of a sphere connects the center of the sphere to any point on the sphere. So this is my radius. Same idea as the radius of a circle. Okay. Right, as long as it goes from the center to any point on the sphere on the inside three-dimensionally, it's the same distance on all of them. All right, what do you think we'd call half a sphere? Hemisphere. A hemisphere is a good, I understand where that's coming from because you got a semicircle, but it's a hemisphere. Okay, so a hemisphere is half of a sphere. Okay, so then we have blank that divides a sphere into two hemispheres. So if we think about the globe, what divides the globe into two hemispheres? The equator is one. What else? Prime meridian. And what else? The axis is going to be like a line segment, right? What is the prime meridian? What is it a line of? It's longitude, right? So is the prime meridian the only line of longitude that would divide the sphere into two hemispheres? No. Actually, any line of longitude would, right? Now that's going to, the prime meridian divides it into the east and west hemisphere, like specifically, but still, it would still divide it into two hemispheres. We just wouldn't have any names. We wouldn't have a fancy name for it, right? What about the lines of latitude? Do all the lines of latitude do that? No, because what happens when we start going up from the equator or down? They get what? The circles get smaller and smaller and smaller. Where all of the lines of longitude, which are actually all circles, all of them are the same size. But for latitude, the circles get smaller as you get closer and closer to the poles. Does that make sense to you? Why do you look confused? Okay, so the lines of longitude intersect at the poles, north and south pole, right? So do you see how when I turn this, this could be any of the lines of longitude because they all intersect at the same point, where the lines of latitude don't intersect each other at all. Does that make sense to you? Okay. So the biggest circle that you could draw on a sphere would be like the equator or the lines of longitude. Does that make sense to you? Now that's on a globe. On any sphere, I could draw a line that looked like this, which this isn't longitude or latitude, right? But it's still the biggest circle I could draw. Okay, so there's, a limited amount on a globe, but an infinite amount on any sphere. Those are the ones that are important to us. The smaller ones, like the other lines of latitude, not so important. But what's going to divide a sphere into two hemispheres is what's called a great circle. Okay, so the great circles are important to us. Okay, so the great circle has the same radius and circumference as the sphere itself does. Okay, so they share a lot of stuff that a circle that's not a great circle would not. Okay, we good? All right, so now the formulas that I'm going to give you today, I'm going to give them to you in the way that you've been given most formulas throughout your math career, is this is it because I said so, and that's what we're doing, right? But I'm going to explain to you the why, but not today. On Tuesday or Thursday, whichever day it is that I see you again, I'm going to show you a quick little animation that explains it way better than I could about where it comes from, because it's not as straightforward as some of the other formulas. So right now I'm just going to give it to you, and it is what it is, right? So plus I don't think they're brand new to you anyway. Volume of a sphere with radius r is 4/3 pi r cubed. Okay? That is the volume formula for a sphere, which again, I will show you where it comes from and why, but right now it's just got to take my word for it. And so now we're going to find the volume of each sphere. So I'm going to write down my formula, 4/3 pi r cubed. What's the radius here? 12. So radius is equal to 12, and we get 12, computer don't, 12 cubed. All right, so although every single question on these notes and this homework you can do without a calculator, you are capable of. I'm going to let you use it for some of them. You should be able to cube 12. I mean, it's no fun, but you're capable of it. But go ahead and cube 12 and tell me what you get. 4/3 times pi times what's 12 cubed? 1728. Okay, so then I want the final answer to be an exact form, which means I'm not using the pi button, but I can still use the calculator. And so when you multiply 1728 times 4/3, what do you get? Okay, 2304, and then what? Pi inches cubed. Okay, now what if when we did that, when we multiply by 4/3, what if it didn't divide out evenly? I mean, we're dividing by 3, not everything is divisible by 3. So if the calculator had given you a decimal instead of the 2304, what would you do? Okay, if you are capable of doing all of this without a calculator, then the pi button is definitely not an option. Putting it over 3, I don't know what it is. Okay, so you can do that. You could like retype it in, and that works, and then put that over 3. But I heard something else too. What would I do? You're using the calculator. I don't want to use the pi button because that I can't do without it. But how do I turn it into a fraction without? You can do it any way. That totally works, and that's fine. What's your other option? Math button. Math enter. And as long as you didn't multiply in anything that's irrational, it'll put it in a fraction form for you. Now let's say what you got was 2/3. Would you write 2/3 pi? No, it's always in one fraction. It would be like 2 pi over 3. Does that make sense to you? It's how you write it is important. In the formula, I know you have the fraction in front of the pi, but this is a formula. When you're done, it's all in one fraction. Okay, that's really important that you just train yourself to write things that way. Okay, all right, but that one came out evenly. So let's look at this next one. I want the diameter of a sphere with the volume of 972 inches cubed. All right, so I've got volume, that's 4/3 pi r cubed. I want the diameter. This formula uses the radius. If I have the radius, can I find the diameter? Yes. If I have the volume, can I find the radius? Yes. So I write down my formula, the whole thing. The formula includes the equal sign and the capital V. Okay, it's an equation. So then you substitute in what you know. 972 pi is equal to 4/3 pi r cubed. Now we're trying to get r by itself. So what could I do here? I can divide it by pi. I'm not canceling out pi. I don't get to get rid of pi. There's no like magic poof and then pi goes away. But I can divide both sides by pi. And when I do that, these cancel out, and so do those. They do cancel out, but you don't get to just willy-nilly go knocking things out, because then that gets y'all in some big trouble sometimes. So this leaves me with 972 is equal to 4/3 r cubed. So now what would I do? Good. Multiply both sides by the reciprocal, which is 3/4. So over here, these cancel out, because that's why we did it. And then 3/4 times 972, then you get 729. Okay. Once you get that far, then put the calculator down and hands off until I tell you to. Now, I don't really want r cubed, right? I want r. And so I've got to undo that. So I want you to listen carefully to my words and just follow the pattern with the words. So if you have r squared and you want r, what do? Square root. So if I have r squared and I want r, then I take the square root. If I have r cubed and I want r, what do you think you do? Follow the words. If I have r squared and I want r, I take the square root. If I have r cubed and I want r, I would take the square root. No. Cube root. Don't just repeat the words. R squared and I want r, I take the square root. Because it was r squared, I need the square root. If it's r cubed and I want r, then I take the cube root. Now I realize you have no idea what that is. But do you see how the words work? Right? So you need to take the cube root. You don't know how and what that means, but does it make sense when you follow the pattern as to what you're trying to do? That's what I want you to get first. Okay. So what we're looking for is this then. When I'm looking for the square root of a number, I'm looking for a number times itself that will give me that value that I have, right? So when I take the cube root, I'm looking for a number times itself that would give me that value, right? Because isn't r cubed just r times r times r? So I want what number times itself would give me that. Now, you can simplify this the same way you simplify square roots, meaning you start your little tree, you do your factor tree. And if you just do the whole factor tree out just like you would when we very first started doing square roots. That's why I wanted you to understand how to do it completely and not just shortcuts, because then the shortcuts don't work on other things. So if I do the complete factor tree, for square roots, I was looking for groups of 2 to bring out. For a cube root, I'm looking for groups of what, do you think? 3, and then the rest works exactly the same way, okay? Now, we're not going to do this by hand, but you can, and it's the same idea. If that was r to the 4th, you'd take the 4th root. If it was r to the 5th, you'd take the 5th root. Now, here's how you write it. When I take the cube root of both sides, then r is equal to, now it looks like a square root, but if I leave it like that, that means the square root of 729, and that's not what I want. So there's a little 3 that goes right here. Because when there's nothing, it's like an invisible 2. It's like when there's no exponent, there's really a 1 there. Same kind of idea. When there's no number there, it's a square root. If that was the 4th root, it'd be a 4. If it was the 5th root, it'd be a 5, and so forth and so on. Does that make sense to you? All right, now let's look at our calculator. So if you, well, maybe. Okay. So you know you can get to square root right here. But if you do that, you're going to get square root, and that's all we want with it. We want the cube root. So the math button, which is right underneath alpha, if you hit the math button, which one of those do you think you want? 4. So that gives you the cube root of, you type in 729, and there's your answer. So now if you take 9 to the 3rd power, guess what? It's 729. Okay? Does that make sense to you? So now I know that r is equal to 9. Am I done then? No, what do I actually want? The diameter. So the diameter is what? 18 inches, or inches squared, or inches cubed. Just inches, because it's something I could go measure with a ruler. Good. Everybody good with that? Any questions? So make sure you don't go through a whole problem like that and then be like, 9, woohoo, I'm done. And not, all you got to do is double it to get the diameter. I know, just like that. Get all the hard stuff. All right, so we're going to go ahead and work through this one together. Also, just in the interest of time, I'll let you punch the buttons on the calculator. But so I want the diameter of the sphere with this volume. So I start by writing down the volume formula. and I substitute in everything I know. I have the volume. It's 36,000 pi. That's equal to 4/3 pi r cubed. So I would start by doing what? Good. Dividing both sides by pi. So the pi's cancel out, the pi's cancel out. Then I can go ahead in the same step without rewriting it. I will multiply by 3/4. You can rewrite it if you want to. You just don't need to. Just don't get lost in what you're doing. So then that means that r cubed is equal to what? 27,000. Okay, and then you need to write this step. R equals cube root of 27,000. Write that down. Some of you get way too calculator happy. You try and do way too much and nobody can follow your work, and then you are not getting credit. You need to write that down. Then you can punch the buttons on the calculator and get R equals what? 30, which means the diameter is 60 centimeters. Okay. Everybody okay with that? Any questions? Alrighty, so now the next one, this is not a difficult problem, but I put it on here because I want to talk about process. Now, if I want the volume of the hemisphere, how do you think we're going to do that? Good. Do what we normally do and then divide it by 2. Okay, that works. But here's what I don't want to see happen, is I don't want to see you manipulating the formulas. And by that I mean, if you need 2 of something or you only need half of it, yeah, you could take the formula and double it and then substitute stuff in, or take the formula and take half of it and substitute stuff in. And there's nothing wrong with that. But what happens then is, if you're already not a formula person and they kind of confuse you when you're trying to remember them, the more you manipulate them, the more stuff you have floating around in your mind, and the more likely it is you don't even have a clue what the actual formula is because you've manipulated it so many times. Does that make sense to you? So it's better for you to use the formulas, go with just a certain small number of things that you understand, and then take the answer and do whatever you want to do with it instead of manipulating the formula. So basically what I'm saying is, if it's not something that you're going to be able to just pull the formula right off the formula chart, like you're never going to see formula chart. Here's a formula for the volume of the hemisphere. Again, not a difficult problem, but you're not going to see that. So don't work it that way. Instead, treat it like a composite figure. Now, you can say take it and divide it by 2. And there is really nothing wrong with that, but I'll show you in a minute why we don't really like that. Instead, how much of the sphere do I want? Half. So it's really the same thing mathematically, but it is going to simplify your life a little bit to do it like this. So really what I want is just half the volume of the sphere. And the volume of the sphere is what I actually have a formula to do something with. So my volume of the sphere is 4/3 pi r cubed, right? So that's 4/3 times pi. What's the radius? 4. So 4/3 pi times, what's 4 cubed? 64, good. So then the volume of the sphere, I don't know, what do I write down for that? Yeah, exactly. So I don't want that, I'm not going to have a decimal times pi. I don't get to now just multiply in pi because I happen to get a decimal. Okay? So what is it? 256 pi over 3. 256 pi over 3 is the volume. It's not 256 over 3 pi. It is 256 pi over 3. Everybody with me? This is the calculator gave it to me. 4/3 times 64. You have what you have right there. Hit math, enter, enter. Bam, there's your answer. Yeah, seems like magic. Okay, so now, do you see why I didn't want my plan to be volume divided by 2? And why we take those formulas and we don't just do like over 2 anymore? Because when I take this, do you really want to take this and divide it by 2? No. I mean, if you have a calculator, whatever, but we also need to understand that you don't always have that. So taking half of it is way better. Half of 256 pi over 3. Now, I know you have the calculator in front of you, but remember, all of this can be done without a calculator. So if you did not have one right now to finish this problem, you could multiply straight across and get 256 pi over 6 and then reduce it. But you're making more work for yourself. Instead, can you reduce before you multiply? Yes, 2 goes into 2 once and then goes into 256 how many times? 128. So in the end, your final volume then meters. There you go. Everybody good with that? So remember, I know there's a lot of things that I say and I try and show you, and then y'all leave here and you do absolutely everything with a calculator, and you never think about it until you get on a test or a quiz, and then you don't have it, and you're like, well, I don't know what to do with that. Well, that's because you didn't practice. Okay, got practice. We good? All right. So here's a biology application. It says giant squid need large eyes to see their prey in low light. The eyeball of a giant squid is approximately a sphere with a diameter of 25 centimeters, which doesn't really mean a whole lot to us because we don't think in metric units, right? We think about like in inches. But it goes on to say, which is bigger than a soccer ball. Let that sink in for a minute. A giant squid eyeball is bigger than a soccer ball. A soccer ball is larger than this sphere I have in my hand right here. Okay? I mean, it's not a ton bigger, but a soccer ball is probably a little bit bigger than this. It's a big, and look at it compared to the rest of its body. I mean, here's the eyeball right here. I don't know how well it showed up on yours, but yeah, that's why they're called giant squid, by the way. So, just saying. But, so imagine you're swimming along and this thing swims by you and its eyeball is big. One eyeball is bigger than your head. Does that freak you out a little bit? Yeah. All right. So now the chances of a giant squid swimming by you, like slim to none, because they live in the deep, dark depths of the ocean that you don't get to swim through. But either way, it's still ginormous. So a human eyeball is approximately a sphere with a diameter of 2.5 centimeters. How many times as great is the volume of a giant squid eyeball as the volume of a human eyeball? Now, there's a few ways to work this problem. They've given me enough information where I can actually find the volumes, but that is not usually the intention of these kinds of questions. It doesn't ask me what the volume of the eyeballs are. I don't even care. I don't need to know that. I want to know how many times bigger is it. Okay, and that was kind of the idea of what we talked about towards the end on Friday. So what we're going to do is we're going to take the information we have. We're going to start with what we had. They gave us the diameters. So I'm going to find a ratio of diameters. So I'm going to take the 25 and put it over the 2.5. And I want to reduce this fraction. Don't touch the calculator, okay? This isn't a super difficult one to do, but you don't like decimals, you don't like fractions, you mix them together, that makes it even worse, right? So you need to know how to handle something that's mixed like this to make it easier on yourself. Now, this would be way easier to reduce if there was no decimals in my fraction. Would you agree with that? Okay, so if I multiplied 2.5 times 2, it would no longer be a decimal. You agree with that? Can I take that and just multiply the denominator by 2? No. I would have to do both of them, right? So if I take this and I multiply it by 2 over 2, okay, then what happens is I'm basically multiplying by a value of 1, so it's fine. So it changes it to 50 over 5. Is that a whole lot easier to reduce? Yes. So do you see how you can manipulate it to your advantage? But you got to be careful that you're not making stuff up and changing values. But now that means that reduces to just 10 over 1. And I'm going to leave it as 10 over 1 because I want to look at it as a ratio. And 10 is still a ratio, but still I want to look at it like that. But so that right there doesn't have a whole lot to do directly with what we're doing right now, but those kinds of things come up. So instead of trying to divide out decimals and messing up on moving your places and making it all kind of crazy hard, and that one you could probably still divide or understand pretty easily. It would be 10 over 1. But if not, if it's something else random, you can always adjust it. I could have also multiplied by 10 over 10 just to move the decimal place, right? That works too. I just felt like 2 was a little bit easier. All right, so now, this is the ratio of the diameters. The idea here is for you to understand what happens to the area and the volume and not necessarily what the area and volumes actually are. So if I'm going to look, we're going to look at the ratio of areas also and the ratio of volumes. So since we're talking about circular stuff, it does make things just a tiny bit easier to understand. So I know this was diameters, but if the ratio of diameters is 10 to 1, if I divide them both by 2 to get the radius, then isn't the ratio of the radius still just 10 to 1, right? So if this is the giant squid eyeball, the radius is 10 times as big as the radius of my eyeball. That's the idea here, right? So if I wanted to find the surface areas, then when you find the surface area, or the surface areas, or I can just think about the area of a circle. That's pi r squared, right? So if the radius gets multiplied by 10, when you substitute it in, not only does the radius get squared, but that 10 gets squared as well. Does that make sense to you? So the ratio of the areas is 10 over 1 squared, which is 100 to 1. Ratio of the volumes, well, if the radius gets multiplied by 10, when I substitute it in, the radius gets cubed, and so does the 10. So it's 10 over 1 cubed, which is 1,000 to 1. And if you think about the eyeballs, I think you can see how this radius is probably about 10 times as big as the radius of what my eyeball would be, right? But does this look like it's about 10 times as much as the volume of my eyeball? Heck no. Okay, I could fit a lot of my eyeballs inside of here, right? Be a little weird to think about, but the volume is way bigger. It changes at a way quicker rate than the radius did. So if the ratio of the diameter, if the diameter is 10 times as much, the surface area is 100 times as much, but then the volume is 1,000 times as much, right? So the volume is 1,000 times greater. So sometimes these questions are asked either without giving you actual values where you can find the volume, or giving you something like this, where the volume of that eyeball would be huge. And so now you're lost in all these big numbers, and then you're confused when you didn't need to do any of that. You just need to understand the concept and how the rate at which things change. Okay, we all good with that? Any questions? All right, good job. So now let's look at surface area. So once again, I'm just going to give you this formula right now. It's because I said so, and then I will show you where it comes from and why in just Tuesday or Thursday. So the surface area formula for a sphere is 4 pi r squared. Okay, there's the surface area formula. 4 pi r squared. So this first one says I want the surface area of a sphere with this diameter. So surface area is 4 pi r squared. So 4 times pi times 10 squared? No? What's the radius? 5. I don't know why my pen is being stupid. There you go. 5 squared. So that's 4 times pi times 25, which means that the surface area is equal to 100 pi feet squared. Good. Okay. Everybody okay with that? I mean, that's pretty straightforward there. All right, so B says we want to find the volume of a sphere with the surface area of 144 pi. So I'm looking for the volume. That's 4/3 pi r cubed. In order to find the volume, I have to know the radius. But they didn't give me the radius, they gave me the surface area. If I have the surface area, can I find the radius? Yes. So surface area is 4 pi r squared. I substitute in what I have, which is the surface area, 144 pi. It's equal to 4 pi r squared. So what would I do here? Good. I can divide it by pi, and here I'm going to go ahead and divide by the 4 at the same time. I didn't write it that way on the other ones because we were dividing by a fraction, so it was a little bit different. But here, the pi's cancel out on both sides, and so do the 4's on the right-hand side. So on the left, I just need to do 144 divided by 4. What's that? Good. So r squared is 36, which means r equals 6. So then I'm going to take that and substitute it in here. So it gives me 4/3 pi times 6 cubed. So 4/3 times pi times 216. And then what do you get for the volume? (288 pi meters cubed). Good. Now, if you were doing this without a calculator, when you got to that point, the 4/3 times 216, what would be the easiest thing to do first? Okay, put it over 1, and then would you just multiply straight across? I would simplify first. So like if you had this 4/3 times 216 over 1, you determine whether or not you can reduce that, because it's either it's divisible by 3 or it's not. And if you can do that, then you get 72, and that times 4, isn't that a whole lot easier than 4 times 216 and then dividing that by 3, right? So remember, look at what you have. Don't just start doing stuff. See if you can, make it a little bit easier on yourself as you go through. All right. Now let's look at this one. We are looking for the surface area of a sphere that has a great circle. Okay, so I need surface area 4 pi r squared. And they didn't give me the radius, but they did give me the area of the great circle. Well, the great circle has the same center and the same radius as the sphere. So I know that the area of the circle is 49 pi. Area formula for a circle is pi r squared. So what's r? 7. Right. So I come substitute this in. 4 times pi times 7 squared. 4 times pi times 49. Oh, sorry, I'm not leaning in. I just does weird things to the board. Okay. Surface area is equal to what? 196 pi miles squared. That is a big sphere. Okay. All right. So I want you to look at this, and I want you to think about substitution here. Did I really, really have to find the radius to do this problem? No, you didn't, because 49 pi is pi r squared, right? Here's pi r squared right here. I could have just substituted that in right there, because that's what ended up happening anyway. That 49 pi came into right there. So when you substitute, it doesn't have to be a single variable. It doesn't always have to be x or r. If you get x squared equals 27 and you have to substitute an x squared in somewhere, you don't have to find the square root and then re-square it. Same thing here. Now you have to be able to recognize that stuff and use it correctly. I mean, it wasn't that big of a deal to find r, but just understand that you can do that a little bit differently. All right. So now let's look at D. D says the radius. I'm looking for the radius of I'm not looking for it. The radius of a sphere is doubled. Describe the effect on the volume. Now, it gives me the radius. I could find the volume like this, and then I could double it and find the volume, and I could figure out what happened to it. Total waste of time. Okay? I don't need to do all of that. I don't even need to know what the radius actually is. If the radius gets multiplied by 2, right? Then the surface area is going to get multiplied by 2 what? Squared, which is 4. The volume gets multiplied by 2 what? Cubed, which is what? 8. Remember that these exponents match the exponents on the units for whatever it is that's changing. Okay? The dimensions that you can measure with the ruler change at some rate. The areas change at that rate squared, and the volume changes at that rate cubed. So the question is, describe the effect on the volume. So we can say the volume is multiplied by 8. Nobody asked me what the volume actually is. I don't really care. I just know that if you double the radius of a sphere, the volume is 8 times as big. The surface area is 4 times as big. Okay. Does that make sense to you? Any questions at all? We're good? Awesome.